you sort of have to wonder why a plant physiologist got involved with air quality, but it came from measuring metabolism of things in pretty large chambers. And then at some point you realize you can measure the whole metabolism of something like Cache Valley. Because it's a closed airshed, it's a more defined airshed than the Salt Lake Valley because of mountains on all sides. So that led to us realizing that we could use CO2 as a tracer gas to quantify atmospheric mixing. And we're still a long ways from a definitive answer to that, but it's a start. And this is one of those projects, you know how you're hiking to the mountains and you see the peak and you think you're almost there, and then a day later you still see the peak and you think you're almost there. And the point is you can see the peak and you know you can get there. It's just a lot more work than it seems. But I want to talk about why this atmospheric mixing question is so important. So here's a really gorgeous picture of our campus with the Wellsvilles in the background. I like to show this because it's not orange there, it's just white, but it's still an inversion. I want to acknowledge my colleague Randy Martin, who I think most of you know, and also Larry Hipps, who is a card-carrying boundary layer meteorologist that's helped interpret this data. This is made possible in Cache Valley, how do we say it on public radio, through the generous support of blah, blah, blah. And so that there are more people in Cache Valley working for environmental instrument companies than anywhere in the world. And with that support from those companies, we've been able to do this donation of instruments and money to make it. So here's the inversion. We know there's minimal mixing during these inversions, but it's not zero. And it can vary a lot from one inversion to the next. If we can get a handle on this mixing, we can get a great handle on the rate at which we're putting pollutants into the air. So you don't have to be a rocket scientist to know we measure PM 2.5, so we'd like to know the size of this arrow right there. How fast are we putting it in? If we knew how fast it was escaping, you can see the easy math. We can calculate the rate we're putting it in. So we have to have a handle on it escaping, and the key to doing that is to make parallel measurements of carbon dioxide. Now the beauty of this is we can model the rate that we're putting in CO2 quite accurately, particularly for a closed valley like Cache Valley. We measure the concentration in the air, and from that data, we calculate the top arrow, and if you get the disappearance of CO2, you have the disappearance of PM 2.5, you can see you can calculate this arrow from the ratios. That's the value of this approach. So Ian just showed you some Google images of Cache Valley. Here's another one. You can also do a transect of the valley, and this is why I'm showing this. You click on Google and it gives you the side view. Our inversions, shallow inversions, are 50, 100 meters deep. Deep ones are at 400 meters deep. This is what they look like in a side view. So we often say, oh, we live in a bathtub. Well, not really. It's a pretty shallow bathtub. And there's the Wellsvilles and the Bear River Range. These are thin skiffs of inversions. But we embellish vertical elevations compared to horizontal elevations all the time. We embellish them on globes, and that's something I talked about in a TED Talk once. So now let me show you what this diagram looks like when the vertical axis is the same as the horizontal axis. This is our majestic mountains, are really, you know how the analogy of the earth is like an orange and the little dimples are all the big mountains. There it is. These are remarkably thin skiffs of air that our emissions are trapped in. And now think about the potential for mixing. That's a lot of surface area to mix. There's not much, but it's a huge surface area. This would be true of all the inversions at least in Utah and all over, we have a bit of a distorted view about the ratio of depth to horizontal spread. Now think about the horizontal movement of gases, PM 2.5 and CO2, under that thin, thin film. These gases are moving at least an order of magnitude faster horizontally than they are vertically, which you can see with CO2. Here's some of the interesting and potentially good news. I took a bunch of slides out of this to shorten it, but this is our PM 2.5 in Cache Valley over the last 17 years. The air quality is getting better. But look at the noise in that data. R squared of 0.26, p-value 0.04. This is cumulative. It's the worst 100 days of the winter. This data is adjusted for snow cover, which is something that I decided we needed to do because we don't control the snow cover, and yet that has a huge influence on whether there's an inversion or not, just because of the reflected radiation and the radiation physics. Here's that same data with not adjusted for snow cover. And the point of both of these is that, yeah, the air's getting better, but we don't have a lot of confidence in the slope of this line. Bryce was telling me the same thing occurs in Salt Lake Valley. In fact, it looks like the slope of the line might be bigger in Salt Lake Valley than it is in Cache Valley. But the air quality is getting better. There's the R squared. If you don't adjust for snow cover, the R squared goes to 0.41. So, but you got to adjust for snow cover to get a better handle on this. So this is good news. But now we take that same exact data and predict the future. And if you're a state legislature, you say, yeah, look at that, do nothing, and we're gonna get it, we're gonna nail it. If you're a scientist, you say, wait a minute, I can fit that data with this line. So we don't have a lot of confidence in predicting the future. But the scatter is not because people drive less some years than others or they heat their houses less. It's because of atmospheric conditions, which we can quantify, and we can reduce the noise in this data and get back to the elemental effects of what we're doing. All the things we're doing, how much do they really help? So here's another view of Cache Valley. That orange spot is our CO2 emissions hotspot. That's where the people live, putting the CO2 in the atmosphere. And now I want to show you, first, using CO2 for mixing is not unique just to mountain valleys. We're doing it all over the planet. This is a model of CO2 on a global scale, and winter turns red. High CO2 is the switches, of course, in the summer. This is on the internet. This all moves. It's a fascinating diagram. If I was smarter, I would have made it move here too. But here's Mauna Loa, Hawaii, right? So our longest track and measuring this. The point I want to make with this is when we model this, we are looking at 1 or 2 parts per million changes in CO2. So we need to have pinpoint accuracy to watch this go up and down on an annual basis. That is not true in mountain valleys. We get changes over hours of 100 parts per million CO2. Big changes in CO2. So we're much easier to measure on a small scale in a mountain valley than they are in the whole planet. So we all know this number is parts per million. That's numerically equivalent to a micromole of CO2 per mole of air. 10 to the minus 6 per mole of air. This is important because when we analyze the CO2, the numerator is how much we're putting in the air, and the denominator is the volume of the air in the valley, which I'll show you in a minute. Here's our stations. This is the contour lines. Bottom of the station, we now have a station at the very lowest point in the valley, Benson Marina. It's a marina with like 6 boats, I think, but people go out there for the wetlands. These are 10-meter towers, so they're taller than this room, so we get up sensors up. They average a large area. That's a Benson. Next level up is where the instrument companies are. And they're 26 meters above the floor. Then the next level up is where downtown Logan is, and people think that's the bottom of the valley. That's 47 meters above the bottom of the valley. Then we have the Utah State University campus, 125 meters up, and then there's our campus station. And then finally we have a station on top of Crow Mountain. It's a peak just north of Smithfield that's 400 meters above the floor. So we had 5 stations to look at vertical profiles of CO2. Here's an example of the stations, and being an instrument person, the types of instruments we use for this are critical. This is looking north. You can see the airport there. There's 3 unique instruments that we have used to collect this data, and all 3 are important. So let me take a zero in on the top of that pole right there. By the way, when we're making these measurements, as has come up in this conference, they're bad weather, big rime frost. We have to heat measurements. This makes it hard because it's hard to heat sensors unless you have power to your station. It's hard to use solar power to make the measurements because of all this rime frost that happens during the worst inversions. Here's the 3 instruments. The first one is a 2-dimensional sonic anemometer, and that's quite different than a traditional cup anemometer because it can measure down to 1 centimeter a second of wind speed. And it also can be heated so it doesn't freeze up. Cup anemometers are terrible in the winter. So there's a lot of air movement underneath that inversion, a lot of horizontal air movement, and we think the air is still, but it's not. And it's critical to quantify that. The second one is a fan aspirated temperature sensor, which gives us not only precise air temperature measurements, but also rapid changes. As there's turbulence of cold air and warm air, there's a lot of change in temperature, so fan aspirated is fast response temperature measurements. And then finally, carbon dioxide. This is an open path diffusion CO2 analyzer, and these 3 we've deployed in all of the stations. Here's some data. This is measured at our Space Dynamics Lab, and this particular data was measured by the network at the U of U Air Quality Lab. They have the longest running data set. This is summer data. No inversions, no persistent inversions, just an inversion every single night. Look at the axis, 400 to easily to 500 ppm every single night, 100 ppm increase in CO2 during the summer. So where does that CO2 come from? People aren't heating their houses. We're not Manhattan. People don't drive their cars around at night. And at first, this puzzled me until being a plant physiologist, and I look at the map of the agricultural community, bingo. All of that CO2 is coming from plant respiration at night. And the models match the measurements really beautifully. The inputs match the outputs. The daytime, the sun comes up, there's photosynthesis, it goes right back to ambient. So we know we're onto something when we have good summertime data with models matching measurements of this. Now let's look at winter. This is August to February. Every day a cycle of CO2, but now you see the persistent inversions over there. But the point I want to make about this, I'm going to blow up the winter here. These spikes are diurnal changes of CO2. Almost every day, the CO2 goes down in the day significantly. It occurred to me, if you were a scientist from Mars coming here and you didn't know anything else, you would say, drive more cars, because in the daytime when there's a lot of driving, the CO2 goes down. So that's because of the meteorology. The inversion breaks up and the CO2 can disperse. This data suggests that we have a lot more atmospheric mixing even in wintertime inversions than we thought. Otherwise, how's that CO2 going down so much? How's my time? A minute 55. I'm going to take you through a couple of mass balance calculations of CO2. That gives me 15 minutes to that?
You started with 15 minutes.
Yeah. In Cache Valley, we can quantify how much CO2 we are producing from combustion and home heating because Questar Gas, now Dominion Energy, has two inlets of CO2 to Cache Valley, and they measure them. And when I got to the right people, they said, here's our data. On the coldest days of the winter, we are putting in from natural gas combustion 96,000 kilomoles a day. Now, all these units are all in kilomoles, comparative units. So we know the CO2 for home heating. Here's the CO2, and this is a breakdown of some of it's from home, some of it's from industry. We think driving is what puts the CO2 in the air. That is not true on cold days. UDEC has estimates of driving, but we have roughly 80,000 registered cars, and if each one's driven 25 miles a day, we only put in 20,000 kilomoles of CO2 in the day compared to 96,000 from the home heating. So the heating puts in a lot more by a factor of 4 or 5. And I had to put the humans in here. They contribute a little, although we had a nice poster over here on humans on a global scale for CO2. So there's the input, 118,000. Here's the volume of air. Below the inversion layer, 39 times 10 to the 11th cubic meters. That ratio should give us an increase of CO2 at 30 parts per million per day. And we see more like 100 parts per million per day. I added in soil respiration under the snow. There's a little bit of respiration under snow if the ground's not frozen. Here's the references. 39 ppm per day is our input, and we see much bigger changes in CO2. And I'm going to close on this graph. This is the measured data of increases in CO2. We don't understand what makes these lines go up so much in the day and come back down so much at night, but I think we can get there. I think we can understand what's going on with this, and by understanding CO2 and atmospheric mixing, we can take a lot of the noise out of that line, and we can start to pinpoint how well we're doing on air quality improvements. So, I'll take any questions.